NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
We hear the announcer counting down the final minutes and the final seconds. All of your senses are heightened. Your emotions are running on overdrive because all of those years of work is finally leading up to this culmination in the project's development life cycle.
8, 7, 6, 5,
and
4,
just kind of
3,
waiting again for that brilliant flash of light. And we have liftoff. And I have to say that on the 24th of February 2009, you couldn't ask for a better day as far as the weather goes. All of us were glued to the screens or the monitors in front of us.
2 minutes into the OCO mission, all systems nominal.
That was an excellent 2 minutes after the launch. You know, this was a great start. You know, the images were perfect. It looks like we had a great first stage taking off.
Stage 1 SEP, Stage 2 ignition, vehicle attitude nominal, power buses nominal. Stage 2 burn will last approximately 70 seconds.
And then I started to hear some chatter, you know, on one of the engineering channels.
Fairing separation, vehicle attitude nominal following jettison of payload fairing.
And there was a trajectory engineer that said they had calculated a negative perigee. That means that the lowest point in the orbit is going to be below the surface of the Earth. And that just meant to me that basically the launch vehicle upper stage was going to fall out of the sky. Several minutes after that, there was utter silence. I think we all understood at that point in time that we had lost the mission. And you know, all of the work leading up to that, the 5, 6, 7 years that all of us had worked to for this single point in time was for naught. None of us treated this like a job. We all treated this like something worth doing. We were committed not only to the mission, but committed to ourselves. And that was the hardest part to really accept. In the day or two after the loss of the original OCO mission, we got together here at JPL, including our center director. We had put together a proposal that we submitted to NASA, which we later called OCO-2. Once we got the go-ahead, we never looked back.
Liftoff of the Delta II rocket with OCO-2.
And OCO-2 has been operating now for nearly 5 years.
The Orbiting Carbon Observatory has now separated from the second stage and is flying on its own.
During development of Orbiting Carbon Observatory number 2, we built the flight unit, but we also built a flight spare. We made some modifications to adapt that instrument for use on the International Space Station as OCO-3. The world is changing, the climate is changing, and the best way to be able to deal with changes is to really understand the problem itself. OCO-3, in conjunction with OCO-2, are going to help us to better understand the problem and be able to put processes, procedures in place on how to cope, not just for today's generation, but for future generations. That's life in the space business. It's calculated risk, but it's a risk worth taking. You have to be bold. You have to be daring. You have to be willing to risk the lowest lows to achieve the highest highs. For me, the primary lesson is don't give up. Keep moving forward. And good things will happen. And all of those good things are going to be much more valuable in knowing what it took to get to that point in time.
Good evening, folks, wherever you are on this planet. Welcome to the Von Karman series live here from the Von Karman Auditorium here at JPL at NASA's Jet Propulsion Laboratory. My name is Brian White from the Office of Communications and Education. And tonight, we look at hope, we look at home, we look at the place where everybody you've ever known has ever lived. This is Looking Home OCO-3 in Science from the ISS. Now, we got a great panel this evening, but they will be the first to tell you that this is a very small part of this incredible, amazing team. While we're talking, you're going to see some images behind us of people doing the work, of the work that's actually happening. But I want to get to our panel because there's a lot of great stuff coming out of them tonight. Leading off, we have the star of our opening video, Ralph Basilio, project manager of OCO-3. And next to him, the Science Data Applications and Communications Manager, Yuen. Matt Bennett, the Project Systems Engineer. And finally, last but certainly not least, Graziela, Keller, Rodrigues, Engineering Applications Software Engineer. Welcome, everybody. Now, Ralph, we're going to start with you because we got so much of you in that video. I feel we should just...
too much, but that's okay.
I don't think we did. How did you, get, not necessarily here, but onto these OCO missions?
Well, it started out as a part-time job, believe it or not. So it was about 16 years ago. And I know it was 16 years ago because I looked on my computer and I found an old OCO file that was dated April 16th, 2003. So it does go back that far. So that was my first affiliation with the OCO series of missions. And at that time, I was working on another spaceflight mission here at JPL. So I was a flight system manager for another Earth orbiting satellite system. And one day, early in the week, our project manager called his staff into the room and said, hey, we got a little bit of a slowdown. We got some budget issues. You know, all of us are going to have to look for part-time jobs and take the pressure off of our accounts here. So we said, okay, that's great. And by the end of the week, all of us on the staff found part-time jobs. So the project manager had some mixed emotions. On one hand, he was quite pleased. He was happy that we followed through on his directions.
You all listened and followed
instructions. Yeah, we all listened to him. But on the other hand, he was a little bit dismayed and probably a little bit saddened that we not only took his order, but we did it post-haste. So there was a sense of immediacy to get it done. Because the following week, I don't think anybody showed up for the staff meeting. So, because we're all working on our other jobs. So with that being said, you know, it was really an exciting time for me back in 2003. That was my first opportunity to work on OCO. And OCO was that was NASA's first dedicated mission devoted to understanding atmospheric carbon dioxide for really the purpose of improving our understanding of the the carbon cycle so that we could better understand the processes that are driving climate change today. And OCO was designed to be the first satellite to have the precision, resolution, and coverage needed so that we can understand where these sources or emitters of CO2 and sinks or absorbers of CO2 are. Okay. Regional scales throughout the world. So it was an honorable endeavor at that time, and it still is.
Very cool. And Karen, you were early on OCO, but you like to point out that Ralph's been doing it longer, if I'm correct. Is that correctly?
Well, no, actually, I'm very proud to say, so last week I celebrated my 18 years at JPL, and one of the first tasks that I had was to support these 4 proposals that we're going through, and they were the ESSP proposals, and OCO was one of them. In fact, I see a familiar face in the audience of somebody that I met very early on, and I got on with these folks, and it's been quite a ride ever since.
So, Karen, I guess I'll stick with you on this. Why Earth? Why did you want to kind of with these OCO missions? And
well, Okay, yes, everything that Ralph said, that it is very honorable, and with my background, I wanted to do it, but I would be lying to you if I didn't say they gave me the job and I just did what they told me to do. so.
Okay. Well, thank you for your honesty here in front of all these people. You were watching this video, and you have this wonderful spacecraft, and then there's an anomaly, and that would be, I know, would be crushing for me. How do you deal with something like that?
It really starts with working on things that are meaningful for you, something that inspires you, something that drives you. And for all of us working on OCO, that was definitely a true statement, that we are all focused on getting the job done. So it was obviously quite devastating when we lost OCO. I think the other important thing about overcoming adversity is knowing that it's a process. You know, nothing happens overnight. And for us, a necessary first step was the grieving process. You know, immediately after that failed launch, we convened our science team, and we had a long talk, and I would say that there wasn't a dry eye in the room. But after that grieving process, however short it was, we all drove back here to JPL, because I remember it was early one morning, our lab director was in the conference room with us, and that meant, yeah, this is pretty serious stuff. We need to figure out what to do here. And we set out to basically assess the situation. What do we know? What do we don't know? And we developed a plan. And after we put together that plan, we set out to do what it took for as long as it took to get the job done. And I think the most important thing for me, the main takeaway, was that, you know, you don't really know what you're truly capable of until you meet adversity. You have challenges. You have these obstacles to overcome. I feel it made us a stronger team after that. And we lost one satellite, but today we have an operating satellite and we have a payload operating on the space station. So we couldn't ask for any more than that.
That's true. That's a good point. Without that, you wouldn't have these other two up there. And I'm going to switch to some of our newer members on the team, Graziela, because the big question that we're going to be getting a lot, or at least as I have a tendency to hear a lot with Earth science, is the why. Can you talk to us about the why of OCO-3 and OCO-2 and the OCOs?
So we care about carbon dioxide because it's a very important greenhouse gas, and it's driving global warming. And as humans, we are dumping huge amounts of carbon dioxide into the atmosphere, mainly by burning fossil fuels. And we are actually the ones responsible for the increase in the concentrations of carbon dioxide in the atmosphere.
Yes, and actually we have a very famous example. Most people have heard of the Keeling curve. And the Keeling curve was actually established by Dr. Charles Keeling back in 1958 for the International Geophysical Year. And it's an important point to look at because if you think about where atmospheric carbon dioxide was in the beginning of the Industrial Revolution, and we usually say it's about 1850. From 1850 to 1958, so it's 108 years, it went from 280 parts per million to 310 parts per million. Okay. And the interesting thing, so that's 30 parts per million in 108 years. From 1958 to 2008, which was just a year before the OCO launch, we grew 70 parts per million. So it was up to 385 parts per million. So basically in the span of 50 years, we more than doubled that amount. And folks should know that back in 2013, that was the first time in human history that we reached 400 parts per million. But if you take 2008 until 2019, we actually grew another 30 parts per million, and this was, 2019, May, we were at 415 parts per million. So what we did in 108 years, we did in 11 years. We grew another 30 parts per million in the same location.
Yeah, and that's not even the whole story, right? There are still missing pieces to this puzzle. For example, not all of the carbon dioxide that we dump into the atmosphere as humans actually stays there and contributes to global warming. About half of it, the oceans and the plants are taking down. So in this sense, they are doing us this huge favor. So things could be worse. of taking more carbon dioxide than they emit. But that's on average, because some years they are capable of taking down a lot more than other years. And it's very important for us to understand the processes that control these variations, because we want to be able to predict what the concentrations of carbon dioxide will be in the future, especially in an Earth that's going to be different from the Earth that we have today. It's going to be warmer, and it will have more carbon dioxide in the atmosphere. And these factors, they have potential to impact the ability of these carbon sinks to absorb carbon dioxide. And the way we have to answer these questions is by getting data, it's by getting measurements.
And I'm not sure if you're showing, you see some of the spots. So Mauna Loa will be an example of one of these spots, and that's great. You have a lot of information there. But what we really need to do is to get this globally, and that's what we did with OCO-2. Basically, you took a very precise instrument and you were able to put it out in space and provide that global coverage. And this gives you an idea of what you saw before with the spots. You're able to see this is actual data, level 2 data that we have for OCO-2. And this information is really important because the folks who are working with the climate models, they're able to take our data and actually incorporate into their models. And you'll see in the later animation, they're able to do the work that they do and get that understanding and trust what we provide for them. And the other thing is also establishing this very important baseline for the first time with the precision that we need relative to the ground stations.
Yeah, and so not only the coverage, the spatial coverage that we see that we can only get from space is important, but we also need an instrument that is very precise. Because while the carbon dioxide concentrations in the atmosphere are high, they are big numbers, we are trying to measure local variations, and these are tiny numbers in comparison, so these are very difficult measurements to make. And we also need to be able to take these measurements for many years, right? So we can really understand what's going on, despite the fact that these missions, they only last some years, right?
Some years, yes.
Yeah. Well, OCO-2 already lasted a lot longer, right? What was the initial
baseline? We have one baseline, but we can't assume that's going to last forever. So that's why when, like you mentioned, we're having the flight spare, now we have the twin sister up on the International Space Station, you know,
yeah.
And that's what we have.
Well, that's a great transition. So the why is important. You've got OCO-2, it's been up there for close to a little over 5 years, and now you've got the twin sister, and you sent the twin sister up to the International Space Station. Matt, talk to us a little bit about OCO-3 and the build and the design and all that great stuff.
Sure. So we really like the space station as a platform for the OCO-3 mission because it offers us a number of advantages. The first is that it's already a spacecraft that's built for us. So unlike on OCO-2 where we had to go buy a spacecraft and integrate our instrument into that, the ISS is our spacecraft. It was built for us with the intent of hosting external payloads that can look at Earth or can look out into space and do some scientific studies. We're flying on the Japanese module of the space station, and this is called the Japanese Experiment Module External Facility, or JEMEF. And JEMEF has a site specifically where you can plug in your instrument, and it gives you the power you need. It has a data interface where you can send instructions to your instrument, and you can get your science data back down. It has a cooling system, so it can help remove the heat from your instrument so that you can stay up there and operate. So it's built for that, and that was one of the advantages that we had of OCO-3, that we didn't have to go out and buy or build a spacecraft for the mission.
You got to save some of that time and energy that would go towards those things. You got the USB essentially on the International Space Station.
That's right. So,
okay.
Another advantage is we didn't have to go out and buy a rocket for this particular mission. So the ISS is scheduling launches to the space station on a regular basis. They're giving supplies for the astronauts, experiments for the crew, and then we basically hitch a ride on one of those already pre-scheduled launches, and that's how we get up to the space station.
Okay. What are some of the advantages of? So that's some of the advantages, but science-wise or working-wise, why the ISS?
So another good reason, another advantage of ISS is that it's in a precessing orbit. So what that means is that when it revisits a site on Earth, a common site, it doesn't do it at the same time every day. So sometimes it can arrive in the morning, afternoon, early evening, and that gives us a chance to sample the state of carbon dioxide across the full daylight cycle. In contrast, OCO-2 is in a sun-synchronous orbit, which means that it is seeing the roughly same spot on Earth at roughly the same time of day. So now we get this new enhanced capability with OCO-3 that we don't have on OCO-2. The other enhancement we have is because OCO-2 would point the instrument using the spacecraft. We can't ask ISS to point OCO-3, so we had to add a pointing mechanism to it. And that pointing mechanism is very agile, and it can allow us to scan large areas in a single pass. So as an example, OCO-2 takes multiple passes before it can scan the entire LA basin. That takes multiple days to do. OCO-3, we can do it in a single pass. So now you get a snapshot in time of what the carbon dioxide state is at any given time of the day.
So we could see what, if it was going over right now, we could see what's happening to...
Not right now.
No,
it's evening. So that was a great question, Brian. Actually.
Somebody could be watching it tomorrow during the day.
That's true. You probably wouldn't see it, but it would see us. And I actually really like your question because one of the interesting facts about how we make that measurement, it relies on reflected sunlight. So the way we make the measurement is that the sun shines down onto the Earth and then reflects up into the instrument. And we know what wavelengths of light that carbon dioxide absorbs. So we call these absorption lines. And what we do is we look at these wavelengths of light that are in the near infrared, and when we see the absence of that light in these very specific wavelengths, that's how we know how many molecules of carbon dioxide are there. We can only do this during the daytime. So OCO-3, OCO-2 can only make these measurements in the daytime.
So that seems like calibrating something like this would be a little hard because you have to have the entire International Space Station kind of on your side, or, I mean, you talk about the calibration a little bit here of this.
Yeah, so one way that OCO-2 and OCO-3 are working together is by OCO-2 helping OCO-3 on its radiometric calibration. Why? Because differently from OCO-2, OCO-3 cannot look at the sun because it's geometric constraints from being attached to the International Space Station. But why do we want to look at the sun, right? So like Matt was saying, what these instruments measure is actually the amount of light that is hitting the detector. And what they register is actually an integer number that we call counts, and that don't really have a physical meaning attached to them, just counts. And it's up to us to give a meaning to this number. And what do? We solve that through a process called radiometric calibration. And what we do is we grab a source of light that we know very well. We know how much light that source is outputting. We know its radiance. And we observe the source of light with our instrument, and we compare the radiance from the source with the counts from the instrument, and we derive these factors that allow us to transform from counts into radiance, thus giving meaning to the reading of the instrument. And on orbit, one obvious choice of a source that we know very well is the sun. So lots of the instruments that orbit the Earth calibrate themselves by looking at the sun.
Okay. Very cool. So that's one of the ways that they're working together is with all that.
And so the point is, with OCO-2 being able to have this precise calibration, we are able to sometimes, both OCO-2 and OCO-3 are able to see the same place on the ground within a certain time span, and then we can compare the outputs of the two instruments.
So these spacecraft, they're sending all this data back. Karen, how would we be able to find and see this data?
Well, now I'm going to put on my cap and do a little spiel for NASA. So we actually archive all the data that comes back. So all the NASA missions actually bring the data back, and they actually go into these libraries, and we call them the archives. And this is something that's very valuable because this is taxpayer-funded effort, and all the data is publicly available. So you would go to the DAX, and you can go in, and you would be able to request data and be able to play with it and use it. I am going to qualify that. There are file formats that you have to know how to work with, but we have people that can help folks with that. But it's publicly available. Anyone can use it, and they can do what they want. And in fact, that's something that we're actually looking forward to, because you were talking about OCO-2 and OCO-3. We're waiting to release the OCO-3 data, but since OCO-2 and OCO-3 will be, it's the same data sets, we'll be using the same algorithm, a lot of the users that's interested in the data, we actually train them with the OCO-2 data so they know how to use it, and then when we release the OCO-3 data, it's not going to be such a surprise for them.
That's wonderful. So this is everybody in this room can get this data today. Would they go to nasa.gov or jpl.nasa.gov or?
Well, I would encourage them to go to, for the moment, it would be oco2.jpl.nasa.gov, and if you go in there, you would see we have some links that will take you there.
So oco2.jpl.nasa.gov. I'll say it one more time. oco2.jpl.nasa.gov. Cool. So this data is ours, and it's not easy to get it. There are a lot of risks that come with a mission like this, as we saw from the very beginning. There's a lot of hope. There's a lot of perseverance that comes in missions like this. What were some of these risks, even here on the ground, for something like this? I'll throw it to you, Ralph. You haven't talked to one.
Yeah. So aside from the technical risks, right? So we're the space business is unforgiving. There are no guarantees, right? So it's all calculated risks. Especially when you're building one of a kind, which is what we did with OCO, OCO-2, and OCO-3. But it's not just all technical challenges. We had a couple of programmatic challenges on OCO-3. We survived not one, but 2 threats of cancellation. And that was a significant challenge in trying to keep the team together and keep them motivated and making sure that we were all still working towards a common goal. And we trusted in the nation's appropriations process to come through for us, and it did. We eventually got reinstated, funded, and we launched OCO-3 on the 4th of May of this year. So we've had a lot of challenges along the way and a lot of obstacles to overcome, but we've had a great team. And, that's one of the greatest privileges, I think, in working here at JPL, is working with a talented group of individuals, working together as a team, working towards a common goal. And for me, that's been a fantastic experience overall. And maybe to tag on to what Karen was saying and Graziela with the science data records, science data product from OCO-2 and OCO-3, they're great on their own, but we're going to have even greater synergy with other measurements that are being made on the International Space Station. There are 2 other NASA instruments that are flying right now. One of them is called ECO-STRESS. So that's the ecosystem spaceborne thermal radiometer experiment on the space station.
There's another one. Like, I don't know what this is, but you riffed that off. That was a hard acronym, man.
There's another one that's also flying in the Japanese experiment module. It's called JEDI, and so that's the global ecosystem. Was that Dynamics Investigation LiDAR system. So ECO-STRESS gives us evapotranspiration. JEDI provides us biomass information. So the one thing that we developed on the OCO-2 mission was actually a bonus data product called solar-induced fluorescence. So we all know that plants grow, but not many of us know that plants glow. And so one of our wavelengths, of the 3 wavelengths on the instrument, we can actually see these plants glowing from space. And so that glow is basically a measure of the photosynthesis efficiency of the plants, which is a measure of the health. So it provides us an indicator, kind of a leading indicator of plant stress. And so we could use our SIF measurements from OCO-2 and OCO-3 and try to correlate them with evapotranspiration measurements from ECO-STRESS and also from the biomass measurements from JEDI. So those are just some of the few things that can come together and really make this a boon for the science community and also the data applications community. I remember Karen and I walked through some cornfields in Iowa, trying to figure out if there was any kind of a partnership arrangement with the U.S. Department of Agriculture, right? So the Agricultural Research Service. Yeah. And that was a great experience for us to be able to understand how we, not just JPL, you know, and our missions, but NASA, can contribute to the success of another agency. And eventually, that partnership can flow down and benefit farmers, people that are looking out for us, people that are interested in food security topics. So I mentioned earlier that you have to find something that you truly believe in, you know, something that inspires you, something that wakes you up in the morning and says, you know, I've got to get into work because I've got to put in a good day and I have to contribute to the success as part of a member of a larger team. I mean, that's what really motivates me. It's OCO-2 and OCO-3 are just small pieces, you know, of greater puzzle.
Something I have appreciated about getting to know all of you, putting this together, has been not just the teamwork and the care that you all have for each other, but exactly that. We're here talking about your mission, and you want to talk about everybody's mission. And it's this. I mean, this is what it's all about. It's a part of a bigger team. Not to sidetrack, but if we did do a lecture on eco-stress, it's on our website, so you can find that one back if you want more information about that. But the way that these really all piece together, it is answering some of the bigger questions rather than it's one data set for a bigger question right now.
I don't know if Karen wants to tag on to that, but you know, these are all part and parcel to us understanding these different processes and how it'll influence climate change in the future.
Well, it's a unique opportunity because if you think about, I mean, it was designed that way, right? The experiment module allows different instruments to basically do what we call almost coincident measurements, because that's something that we worry about in science is when you start combining data sets, or even if you're just looking on its own, everyone's thinking, where are you looking at? What's the time of day? And you want to start combining the data. That's something that's really important. And you can ask any of the modelers, they're going to go, there's like, oh, can I use this? This is right. And when you pretty much give them the measurements packaged in a way that they say, oh, okay, this part is already good, I know that, so how can I work with it? There's just a confidence level that's really important. And in fact, in a few weeks, there's a really large science conference. It's called the American Geophysical Union. And OCO-2 and OCO-3 we're putting together a workshop. And we actually invited our colleagues from EcoStress to participate with us. And we're actually looking at how we can look at the data together, what makes sense, what doesn't make sense. And this is going back to what I said, you know, by looking at what they can together when we do the training, when we teach people how to use the OCO-2 SIF data when they're ready. They'll know how to use the OCO-3 data, and they'll be ready to explore how else to use the other data, either from EcoStress or eventually maybe even JEDI, because JEDI doesn't have what we call a temporal aspect because they're actually putting together a biomass map at a very high resolution at 1 kilometer, and there really isn't much change, we think, over the forest in the course of a year, but we don't have a baseline like that. So going back, OCO-2 set that baseline, OCO-3 will continue it. EcoStress is providing that temperature data to look at the plant stress, and then JEDI being able to form the biomass the biomass maps that we need. Just being able to look at all of that together, folks that are studying biodiversity and ecosystems, this is really a jackpot for them.
And you're also, what you're talking about with getting the information out there, but teaching people, you're creating earth science literacy. You're trying to get people who know what they're looking at rather than
for the scientists and also for the public, because there's always a general assumption that folks, they'll just know how to use the data. And that's not true, because not everyone's trained to work with remote sensing data. You can have a PhD and you don't know how to work with our data, but you don't need a PhD to work with our data. And it's just knowing what to do and then going forward, and as I like to say, play with the data.
Play with the data, cool. Now, speaking of playing, Matt, some of these photos and videos, it looks like you're having a lot of fun building the spacecraft. Obviously, it was something you enjoyed. what didn't go this fast.
No, it did not.
What were some of the I guess the risks of the full assembly? We were talking about technical a little bit. Was it smooth besides the kind of delays? Was it a smooth process?
Yeah, overall I think it was smooth. You were asking about risks, and one of the early risks, very low likelihood that this was going to be a problem, but something we worried about was that we were inheriting this twin sister instrument from OCO-2. It had been in a storage container for over 3 years, so we were really anxious to find out how well was this instrument going to work when we pulled it, out of that giant bin in the high bay. And we were really pleased when we put it into thermal vacuum and we started doing performance testing on it. We were seeing that it was functioning really well, so that was a risk we were really happy to retire. Another risk, I think you have a picture of it up here, Brian, from the vibration test.
Let's see. Once again, lots of pictures of the team here. Did I go past it? I went the other way.
Yeah.
We're great at landing on getting Earth science.
There it is.
There you go.
Yes. So this was another, of course, scary test, even though we'd done all the analysis to prove that this was going to work. So when we fly on a rocket, we have to prove that the instrument's going to survive that launch. And so we put it on a table that shakes the instrument as if it's going to be shaken on the rocket. We call it a random vibration test. And so this is a picture of that test when we did it. So one of my favorite stories from this test was that if you see that long bar that spans horizontally from left to right, that was a late design addition that we found out we needed in order to survive our ride on the rocket. And the way that thing works is it's compliant. It's like a aircraft wing. When you fly, you can see aircraft. That thing is supposed to bend in order to take some of the loads from the rocket and reduce the punishment on our sensitive optics inside the instrument. And so I was present for that test. And I can't tell you that was the scariest test I've ever observed in my life, because we're seeing our instrument, our baby, being shaken very hard. You're seeing this thing bend, and you know that it's supposed to, but it still scares you. And when we got out of that test and then we tested the instrument and proved that everything was working fine, that was a huge relief. So that was a retirement of, again, a very low likelihood risk that we had done something wrong, but it felt good to get past that milestone.
Is this a common term? You're saying a retirement of risk. You've used the word retirement that way, and I've never heard it used that way. I'm going to start using it in my everyday life now. That was a retirement of risk after that one.
There's no risk to your retirement, Brian.
Okay. Well, you talked about these delays and these lessons. This is something I've noticed with your team a lot, is you share with each other. Everybody takes their own blame, or not takes their blame. Everybody's accountable in this team in particular. And Ralph, we talked about how there are few people on this planet that have experienced what you have. I think you could count on a couple hands of people who've had that moment. And this goes for everybody, though. If there's lessons or something that you could share, there's some younger budding engineers and scientists in here, but also people who've been here for 30 years. If there's any advice or lessons that you have learned from these experiences.
So I mentioned it before that space business is unforgiving, that there are no guarantees. Everything's calculated risk. So I always say that project management's just risk management. That's what it is for me. And so the thing is that you can put together a perfect plan, but how many perfect plans get executed, the way it was intended to? So there's a famous person out there that said, everyone has a plan until they get punched in the face. So that was Mike Tyson, the champion boxer. But he was actually profound, because you have to understand that all the best laid plans could be for naught. So you have to develop contingencies or off-ramps. Because for us on OCO-3, we didn't get punched in the face once. We got punched in the face twice, right? Okay. With 2 threats of cancellation. But it's being able to make sure that you've got the resiliency and to understand that, this happens. I think after our second cancellation, we figured out how to do this the first time. We just let it roll off our back. But, that you mentioned something about the team. I think it all starts with mutual respect and having a commitment to the mission, and also being committed to each other and holding each other accountable, And I don't think I set foot in any meeting where We were stepping on each other on conversations or discussions. Everyone had an equal voice, and I think everyone felt that they could be heard. And in the end, we all made a decision that was right for the project. And so that was great. And those are the moments I live for. You know, many of us here at JPL, we're not here to be billionaires or anything like that. We're here to contribute to the success of a project or a mission, the institution NASA, and to provide a value to the American taxpayer, the world at large. And being able to work on a team has really been, those are the most precious moments for me, to be able to reflect back on the dozen missions I've worked on my 30 years here at JPL. Those are the special things that I remember. You know, being able to, you can see people finishing each other's sentences, or you know what the left hand is doing, you know, and it's really, those kind of special moments are, I think, it's really part and parcel to being here. JPL is a special place, and the people that work here are special.
I don't even work for you, but you always make me get me charged up. Like, yeah, let's go. What are some other lessons that anybody was making on the Graziela? What's something a big thing that you learned on this one?
Well, mine is not exactly comparable to his, because I have been working on this team for only 1 year. But the story I have to tell and was stressful for me and taught me something was the tale of the brightening lamps.
The tale of the brightening lamps, okay.
Yeah. So OCO-3 carries onboard calibrators, lamps, that we know very well, and we look at them in order to figure out if our instrument changed in any way. Right, so you can imagine how important it is that our lamps are very stable, because we need to know if when we look at them, did they change? Did our instrument change? We need to be able to tell. So we need them to be stable. And I wrote a lot of the pipeline that processes that data. I spent months writing it. And I was very excited after first light to finally have data to put through the pipes and look at the results. And when I look at the results, we are registering radiances that are 15% higher than we were seeing in pre-launch, which is very unexpected, and we were super puzzled. And we could think of 3 options that would explain that. First one, the lamps actually brightened, which isn't great, right? We need them to be stable. The second one is the lamps did not brighten, but the instrument became more sensitive. That would be a big jump in sensitivity, but that's not a problem. That's what our calibration is for. The reason for calibration is to account for changes in the sensitivity of the instrument. So that wouldn't be a problem. The third one, and which was the first one I thought of, was I must have done something wrong. And back then, we didn't have a lot of data to actually tell which one of the 3 it was. And we were having trouble with data corruption, so it was very possible that it wasn't going well with the pipeline, right? That those few values and stuff that we had to take into consideration. So what I did was to obsess for weeks about finding the bug. I even had a dream once that I knew where the bug was. And I woke up in the middle of the night, fought JPL's VPN to be able to connect, and went to the code and rewrote part of it and got the same result, wasn't it? Okay, so eventually we got enough data and we figured out it wasn't a bug, because we were seeing other behaviors that I couldn't possibly have created by myself with a bug. And we also found other evidence that the lamps had indeed brightened. So we had to invent a workaround, and we did. But what I learned from this experience is that this work that we do for these missions, it's very complex, and it's very prone to mistakes. There are a lot of places where a mistake can be hidden, and you are forced to work very carefully and check your work many, many, many times, even if it's to, in the end, find out that you did not make a mistake. But this ghost of, maybe you made a mistake, It's constantly walking with you, and you have to learn to accept its presence there.
Live with the ghost. That's the
Live with
advice
the
to the
ghost. Maybe it's a bug.
Maybe it's a bug. Maybe you did it. But also you were owning that too. That could be a possibility.
Yeah, as I imagine, nobody wants to make a mistake, right? Especially if it affects the work of other people.
Yeah.
Imagine you stand there and you tell people, well, the lamps brighten, and then you find out it's a bug. The lamps didn't brighten.
Well, I'm glad you did. I'm sorry about the dream, but but I'm glad you went through that. We're kind of closing up on what we're going to talk, and then we're going to open it up for some questions here in the audience. While we're kind of showing these final images behind you while you're talking, you're seeing the kind of final end of when it gets to the International Space Station and all those cool moments. You feel like a family. You feel like a positive group, no matter whether you've been here a year or longer than that. Ralph, you talk about your pride in this and your pride in the project, but also the work we do here at JPL. What is everybody most proud of with this mission as we kind of see these images of this hovering over our planet like this, hovering over home?
Well, you have the pride in the mission because of, I know for me, it's what it's doing. It's actually, and I'm going to go back, having that baseline and that data record that wasn't there before, that's a first. And being able to do it with an amazing group of people that you call another family, it's a great feeling. And it's one thing I've been able to pass on to my daughter, that she's never seen me say, oh God, I have to go to work. It's always like, okay, hurry up, we gotta get to school, my mom's gotta get to work, because I want to go to work. And it's a great thing to be able to pass on to your child, to be enthusiastic and happy at work. And I'm going to take this moment to say, I would not be as excited each day if I didn't have a fantastic manager. And with the pride that Ralph has shown and the trust that he's had in us to do our jobs, to not be afraid to come to him and say, hey, I have this idea, I know this is crazy, but what do you think about doing this for applications? And he was like, okay, prove it to me that it's worthwhile to do it. And you go back and say, oh crap, now I got to come up with how I'm going to do this. And he lets you do that. And it's a wonderful feeling. So thank you, Ralph.
Thank you. I'm certainly proud of this team and what we've accomplished. There was, kind of going along with what Karen was saying, there was no challenge that this team said, I don't know how to solve, right? If we had a problem, the team would work late nights, come in on the weekends, whatever it took to get us past that, to keep us moving and ultimately up to the space station. And I couldn't be prouder to work with this group of people who had the can-do attitude. We're not going to let anything get us down. Whatever that problem would be, technical, programmatic, we're going to get this thing up to the space station. We're going to make this measurement. And I'm certainly grateful to be a part of that team.
Well, I'm very proud that I'm doing work that has an immediate impact in our ability to reach our scientific goals. And our scientific goals are something that everybody should be proud of, because they will give us knowledge that will be important for us humans as a society, and even for our future as a species, since they inform us so much about something that is threatening for us, which is global warming. And I think the work that we do is amazing just because of that.
Cool. Ralph?
It's work on these endeavors that improve our quality of life on Earth. I mean, you opened up with this, that everyone we've ever known, they've lived on planet Earth. And so this would be the only home many of us, most of us, will ever know. So the work that we do is part and parcel to making sure that we take care of Mother Earth today, that we're good stewards, that we could hand something down to future generations, our children and future generations, that we're proud of. And that's the main driver for me. And in the end, I am a firm believer that, it's really the team, the people that you work with. Yeah, you need the hardware. Yeah, you need the software, but who develops all that? Who tests that? Who operates all that equipment up there in space? So it's those precious moments working with the team. And I think when my career is over here at JPL, when I walk out the door for the last time, it'll be those moments, those teams I've worked with that I will carry with me as, the most memorable memories from my experiences here at JPL. And I'm proud to be part of the JPL community, proud to be part of, the OCO-2 and OCO-3 teams.
Very cool. We're now going to open it up for your questions. And I know there are a few of you online. You've been asking questions. Those are going to work their way up here. If you do have a question, I just ask that you step up to that microphone right over there. We'll get to as many as we possibly can. And if we do not get to your question tonight, please don't fret. They're going to hang out for a little bit. You can come on up and ask some questions. All right, number one.
Thanks for a great talk. I had a two-part question. First one was, with your vantage point on this data set, how do you see this data set playing forward in terms of ramifications of our understanding of climate change and how that will play out over the next little bit? The second question is programmatic. With the eventual change of the ISS to private operation, how does that impact OCO-3's future and future missions along those lines?
I'll take the first part of the question. We have modelers that's on the science team. So those are the folks that we know if they trust the data or not, because they'll tell us if it's not good enough. And that's what we're getting to right now. You're always fine-tuning. I think that we are seeing and feeling changes. Now we just need to be able to have those models, have those models show us what we hope to see. Because right now, I think we're quite good with what they're trying to do is predict what happened in the past. They take the data and it's like, we know what happened. Is it doing the same thing? What we eventually like to see is when the models can start predicting what will happen to the future. And there's no better way to have that than to have our kind of data set that's really precise and be able to help them with that. And we'll just keep working with the scientists that do that.
Can I also just tag on to that? So maybe a couple of specific examples. So on OCO-2, El Nino, 2015, 2016, we were able to see from our global perspective that there was an increased amount of CO2 being emitted to the atmosphere during that El Nino cycle. And it looks like those emissions were coming from South America, Africa, and Southeast Asia. And what we understood from doing a little bit more research, we found out that South America was dry. Africa wasn't just dry, but it was hot. And Southeast Asia was basically on fire. And so all of those data sets, including the ones that we got from OCO-2, helped us understand what was happening today. Now, as far as for the future, so here's a data applications example, and I'm sure Karen will resonate and she'll remember this, that the lab director for the National Lab for Agriculture and the Environment, Jerry Hatfield, a few years ago when we were in Iowa, he enlightened me. So we were talking about, well, how can we benefit people in the future and producers, farmers. And I think it was after one of these walks in the cornfield. So the interesting thing for me was that, he was excited to be able to say, look, if we get remote sensing data from OCO-2, combine it with our ag research service data, we can provide better advice for farmers, producers, so that of these 25 varieties or hybrids of corn, we can advise them what to plant next year based on forecasts, predictions. And that was exciting, for me, that it's not just serving the needs of the science and research community, but also people in, that are interested in science data applications and informed decision making. And then the second part of your question, I think is just really quickly, is that for me, competition drives out the best in people. So if they're talking about privatizing the space station, we've actually seen a lot of benefit in the launch vehicle arena. 20, 30 years ago when I first started here, we always talked about what's the cost of launching a brick into space. And it was a lot back then. But you have a lot of competitors out there now. So Elon Musk, and Jeff Bezos out there that are driving the cost down for access to space, which allows NASA to have more money to develop science instruments to produce data and information that we need. So I think it's actually a good thing that we have private industry involved in this partnership. Does that answer your question or help answer your question?
Pretty much, although it was about privatization of the ISS.
Yeah.
So specifically for OCO-3, we're a 3-year mission, so we'll be done in 2022. There's already another instrument that wants to take our spot on the space station, so we'll be out of there before the privatization takes over. So answering your question specific to OCO-3. Yeah.
Thank you.
We are going to move on to our next question. While you're stepping up to the mic, actually a good segue. This is from Tyler from YouTube X. What's the expected lifespan of OCO-2 and OCO-3? So you said OCO-3. What's the lifespan of OCO-2?
OCO-2 was a 2-year mission, and we launched in 2014. It's now 2019. We're still going strong. Right now, there's no indications of anything that's going to prevent OCO-2 from not operating for a while. That's right. We've got ample fuel on board. The instrument's still going strong, so we want to use OCO-2 for as long as we possibly can.
Yeah.
It seems that your sensor is a passive sensor, and since you integrated onto the space station, can't you take an energy source and turn it into an active sensor and double its effectiveness and use it during the night? And in fact, if it turns out to be a viable idea, you have my permission to take it and run with it.
You can steal his idea, but can you turn the passive sensor into an active sensor?
So I think the short answer for OCO-2 and OCO-3 is no. So it definitely is a passive sensor looking at spectra of reflected sunlight. But NASA has been involved, JPL has been involved in.
Using the sun, you can do an emission that would stimulate the atmosphere and do the readings at night.
We'll let Ralph keep answering this question, though, so go for it.
Well, there are systems out there that are being developed that could operate at night. And I think there may be airborne systems that are already trying to do that. So those are active sensors. But trying to convert, if you will, OCO-2 and OCO-3, can't do that, unfortunately. Just different technology.
But thank you for the suggestion.
Yeah.
Ron, while you're stepping up, Ron is asking from you two, what is the one factor about this mission that still stands out to you today? Silence.
There's so much to think about. Yeah. I mean, it literally was, as Ralph and Karen were talking about how long they've been on this mission. I also went back in my emails and found out that I've been on this mission since 2011. So, there's a lot of data to sift through.
How about this? We're going to give you a chance to think about this one, and we'll move on to our next question. Yeah.
First off, I'd like to say thank you for the wonderful night. This question goes more so to Karen and Graziela. I'm running a chapter of the Society of Women in Space Exploration on my school's campus, and I just had a question for you. What advice do you have for young girls, and specifically just the future generation of students who want to take on projects like this with NASA?
When you say take on, you mean working
Yeah.
here? Okay. Well, first of all, it's fantastic that you're doing that. We need more women doing that, so I applaud you. You have to just keep studying. You have to study and be prepared and apply, and just know that. And I'll let Graziela speak also. I was very fortunate. I came here and I started working with a great group of people and very supportive, and I encourage any woman to come here and apply and work here and keep studying. we need more women in STEM.
I agree.
Yeah, I think first thing is to be aware that you can go into STEM, choose a field you find interesting, and study a lot. I did undergrad, master's, and PhD degrees in astronomy, actually, back in Brazil, where I'm from. And I wanted to work for NASA, right? But I was in Brazil. So I had participated in this program that sent me 1 year to the United States during my PhD. And so I met some women that were actually doing work for NASA. And when I finally finished my PhD, I just asked them, can you please send my resume around? That's what you got to do. You need to meet some people and be brave enough you can do it, to send your resume, ask them for help. And eventually someone hired me to work on space missions. And that's how you have to do it.
Thank you so much.
One last question. Yeah, that was great. Oh. See, she asked a question, she already got a business card. There you go.
That was my question.
This is the last question of the day. That was your question,
Yeah,
too?
that was my question, but I also wanted to ask, for the other people on the panel, what steps did you guys take to get to where you are today? Like, what started your career here at NASA?
So I can take that one. When I was in undergrad in college, I remember seeing the first video come out about the Mars exploration rovers. And I was just blown away that JPL sent 2 robots to Mars to drive around, and the engineering challenges that it took to get there. And I'm like, I really want to go work here. And one of the things, some of the things I got into in college were projects at my university. And one of those projects was to build a small satellite. They call them CubeSats. So I started one in my undergraduate university. When I went to grad school, I eventually got the opportunity to build one that did fly in space. And that was an incredible opportunity. So one of the advices I like to give people as they're coming through their education and trying to figure out how to work in an engineering aerospace field is to try to get involved in projects as much as you can. Get that hands-on experience. How you apply what you learn in the classroom to projects is huge. And that'll be something that'll help you as you go into the employment field.
Cool. Thank you.
Well, folks, if you're in line, you can come up and ask in just a second, but that is all the time that we have for tonight. First off, a couple housekeeping things. We'll be taking December off, but please join us in January as we say farewell to the Spitzer Space Telescope as it prepares for its end of mission, also happening in January. I'd like to thank our panel one last time for joining us tonight. Can I give a big round of applause for them? And thank you to all of you for joining us today. Have a great rest of your night wherever it leads you. Thank you, folks.